Here we are going to describe these Kohn-Sham equations, which actually are the basics, the key elements in the Kohn-Sham method. So let me remind you of the basic result we have within this Kohn-Sham method. The ground state energy of the system, we can get this ground state energy of the system just minimizing all this functional here with respect to this single determinant wave function that we were using to describe this non-interacting fictitious system. Let me remind you the basic what we're doing here in this Kohn-Sham method. We're replacing or we're decomposing the total functional or the universal function of the system with a two component. One was the kinetic energy functional of this fictitious non-interacting system, and then the rest, which was the Hartree exchange correlation energy functional. I'm minimizing with respect to the density, and we could use doing this procedure of this Kohn-Sham method. We could use its equivalent to minimize with respect to the single determinant wave function. The density we can get from this minimization actually is going to be the ground state density, and of course, because these two are going to be the same, but of course we need a good approximation for this Hartree exchange correlation energy functional. And minimizing with respect to the density, we're saying that we are getting the ground state density, and just plugging the density here, we can get the ground state energy as well. So basically, the result we were getting is that instead of doing the minimization with respect to the density, we could do the minimization with respect to this single determinant wave functions that we're using to describe this non-interacting electron system. So this single determinant wave function, this one, which is basically this Slater determinant, is constructed from a set of n, because we have n electrons, orthonormal occupied spin orbitals. So here we have this one electron wave functions that of course depends on these spatial and spin variables. And so we are going to first build that single determinant wave function just using that occupied spin orbitals. And these occupied spin orbitals, they are usually taken to be eigenstate of SZ, because as usually here the Hamiltonian is going to be independent of the spin. So we can split that one electron wave functions in these two contributions, the one which depends, it's associated to the spatial variables, and then it's the spatial component, and then we have the spin component. The spin component usually is going to be spin up and spin down. So basically, the analysis we're going to make here in order to find that minimization procedure, it's going to be parallel to the analysis that we made in the Hartree-Fock method. Because in the Hartree-Fock method, actually, we're doing the minimization with respect to this Slater determinant. We're using the Slater determinant to build the wave function to describe the system, and then we were doing the minimization with respect to the components that we were using to build that Slater determinant. So here we are going to do a parallel analysis to this one. So what do we have to do here in order to do the minimization with respect to this wave function psi? So first we need to build the Slater determinant using that spin orbitals we have here corresponding to for each electrons, the same way we did for the Hartree-Fock method. So once we have built that Slater determinant, then we can write the total energy in terms of these spin orbitals and sum over the spin variables. So we need an expression of this total energy. We're going to call the total energy this term here. So we have to do the average of this one, the average of this, the kinetic energy and the external potential, considering the Slater determinant here. The same way we did for Hartree-Fock method. And after doing that, that's the expression we have. This is the average for the kinetic energy and the external potential here as a function of these spatial orbitals we are using to build that Slater determinant. And besides that, we also have another component here, which is the Hartree exchange and correlation function, which depends on the density. And this density at the same time, of course, depends on Slater determinant we are using. And this density here we can't write in terms of these spatial coordinates that we are using, or this spatial wave function we are using to describe the one electron wave function. So that's the electronic density as a function of these states. So therefore we have an expression here which depends on these one electron orbitals. So once we have that, what do we have to do? We have to do the minimization procedure. And the minimization procedure is going to be the same, it's going to be parallel to the one we did again for the Hartree-Fock method. The minimization over that Slater determinant can be recast into the minimization of this functional we have just defined, which depends on these one electron orbitals, with respect to these one electron orbitals, with the constraint of keeping the orbitals orthonormal. So the same way we did for the Hartree-Fock method. And for that, we know that we have to use the Lagrange multiplier method. So we have to define a new functional here, which basically is the energy we have just defined. In this case, we are going to call the new function, we are going to call it L. And this new function is going to be the energy we have just defined. And then we have another term where we have the Lagrange multiplier, epsilon I, and times the constraint for each electron state here. The constraint is associated to the normalization of the one electron states. And we have to sum over all the different orbital states that we have. In this case, we have n orbital states because we have n electrons. So this is the new functional we are going to define. And now, using that functional, we have to find the minimum of this functional with respect to these orbitals. The way of doing that is doing the functional derivative of this new functional L with respect to the Ci complex conjugate, the same way we did again with the Hartree-Fock method. And if we are doing the functional derivative of this L functional here as a function of Ci complex conjugate, we have the first term here, this one, plus we have another term here, which is the functional derivative with respect to of the energy function of the Hartree exchange correlation energy with respect to this Ci complex conjugate. This all it's coming from this term here, which is going to be equal, and this term here is coming from this Lagrange multiplier here, epsilon I times Ci. Okay, this is the result we have of making zero, because we are looking for the minimum, making zero the functional derivative of L with respect to Ci complex conjugate. So this is going to be the equation that the Ci has to satisfy. So this is the equation that we are going to need to solve in order to find the Ci and the epsilon I. But before doing that, we are going to work more on these functional derivatives here, because here we have the functional derivative of this Hartree exchange correlation energy functional with respect to Ci complex conjugate, but this functional depends on the density, and we are doing the functional derivative with respect to, not to the density, but with respect to the Ci complex conjugate. So how we are going to do that? We are going to apply the chain rule, because we know that the density depends directly with this Ci complex conjugate, the way defined before. So here we have, that's the relation between the density and these orbitals we have. So we are going to, in order to do the this functional derivative of this functional, which depends on the density with respect to this Ci complex conjugate, we are going to apply the chain rule. And when doing the chain rule of this in the functional derivative, we have to do in the following way. We are going to do the chain rule with just applying with respect to the density. So we are going to do, in order to do this derivative, we are going to do the following. We are going to calculate the functional derivative of this functional with respect to the density at evaluated at r prime times the functional derivative of the density evaluated at r prime with respect to Ci complex conjugate evaluated at r. And then we have to sum, in this case, in place to do the integration over all different possibilities for r prime. Okay, this is the chain rule that we are going to apply in order to calculate that functional derivative here. This contribution, this second contribution here, it's going to be very easy to do. It's straightforward, and the resulting functional derivative of the density with respect to this Ci complex conjugate evaluated at r is just this term here. So if you substitute this one with this one and plug it here, and make the integration over r prime, which because of this, the presence of this delta, it's really simple, then the functional derivative, the resulting functional derivative is this one. As you can see here, that's much more straightforward, because in order to calculate that functional derivative, it's the resulting, after applying the chain rule, is this one. So we have to do the functional derivative of the energy functional with respect to the density times the one electron state. So, and actually that functional derivative of the Hartree exchange correlation energy with respect to the density is going to be a potential. We're going to call it Hartree exchange correlation potential, and we are going to write like as a VHXC, which is going to be dependent, of course, on the density evaluated at r. So now we know that expression. We're going to substitute all of this we have here with this result here. So we are going to plug this one here, and when we're doing that, then the final result we have is this one. So this is the equation we have, and we need to solve in order to get the one electron states here and the epsilon I, which are the Lagrange multipliers. So these are the equations, the orbitals that are going to minimize the energy we have defined before. And actually, as you can see here, and as it also happened in the Hartree-Fock method, it looks like a kind of equation we have to solve the eigenstates of the Hamiltonian, the eigenvalues of the Hamiltonian. It looks very similar, actually. And actually, the equation we had for the Hartree-Fock equation, it was a bit different in the sense that we didn't have such kind potential, because here we're using a functional expression for this Hartree exchange correlation energy. In this case we didn't have, and instead of this one we had a Hartree contribution and a non-local exchange contribution. So that's the main difference we had with respect to this Hartree-Fock method. But now we are centering the analysis in this Kohn-Sham method. These are the equations again that we need to solve in order to get that one electron states, and using that one electron states we can build the Slater determinant, and then we can get everything. And actually, because this equation, it looks very similar to the equation for the Hamilton, for the eigenstates and eigenvalues of the Hamiltonian, that orbitals here, they are called Kohn-Sham orbitals. And with these Kohn-Sham orbitals, we can build what's called Kohn-Sham wave functions. The Slater determinant, when using that Kohn-Sham orbitals, is called the Kohn-Sham wave function. These epsilon I are the Kohn-Sham orbital energies. And the sum of these potential here, the external potential and the Hartree exchange correlation potential, It's called the Vs, which is the Kohn-Sham potential. So these Kohn-Sham equations here are a set of coupled self-consistent equations. They are self-consistent equations are coupled because that potential here, this Hartree exchange correlation potential, which depends on the density, but the density depends on how we are getting the density. The density is the sum for all I of this contribution here. So we need these functions in order to build the density, and once we have the density, we can build this one. So in order to have the equations that each Ci is satisfying, we need the result in order to build that one. That's why these equations are self-consistent equations. Actually, it also happens in these Hartree-Fock equations. They are coupled self-consistent equations. These equations define a system of non-interacting electrons. Of course, then with this one, with this state we can build the Slater determinant in order to get that Kohn-Sham wave function. So that are the equations that correspond to these n non-interacting electrons. And these n non-interacting electrons, they are moving in this what we can call effective potential, which is the sum of these two potentials here. And we are calling it the Kohn-Sham potential. And everything is built so that the ground density, the ground state density that we can build once we have these Kohn-Sham orbitals is the same, of course, as the exact ground density, the exact ground state density corresponding to the physical system, to the real system of these n interacting electrons. Not only that, we know that besides that, the ground state energy of the physical system can also be obtained once we have that one electron orbitals satisfying these Kohn-Sham equations. The exact ground state energy is obtained just using that expressions. When we have that, we are plugging these Kohn-Sham orbitals satisfying that equations in these expressions we had right before here, and then yes, if we are plugging that the resulting one electron orbitals we are plugging here, we are getting this total energy of the system, and the total energy is going to be the ground state of the physical system. So here we have derived, this is the very important result, the key result in the Kohn-Sham method, we have derived the Kohn-Sham equations, the equations that we need in order to build the ground state density and the ground state energy. Of course, in order to have that equations, we need some approximation for the Hartree exchange correlation energy function in order to get from here the Hartree exchange correlation potential. And but that's going to be for next. But once we have an approximation, a good approximation for that, then we can build these equations that we need to solve in order to get the ground state properties of the physical system.